Hello and welcome to today's lecture on analog transmission. This is the second lecture on this topic, and in this lecture we shall cover these following points. I shall give a brief introduction what we have discussed in the last lecture on the same topic. After that, I shall introduce to you the basic concepts of angle modulation, and essentially we will see angle modulation involves two types of modulation, frequency modulation and phase modulation. Then I shall discuss the relationship between frequency modulation and phase modulation. Then we shall consider the bandwidth and power required for FM and PM transmission. Then we shall switch to a different topic, basic concepts of digital data to digital signal conversion, where there will be three different types. First one will be amplitude shift keying, and we shall consider in detail the various issues related to amplitude shift keying, particularly frequency spectrum of ASK signal, the power requirement for transmission of ASK signal, and also we shall discuss about the frequency and phase shift keying. Then we shall end our lecture with applications of different types of conversion technique, digital signal conversion techniques. And on completion of this lecture, the students will be able to explain the basic concepts of angle modulation. They will be able to distinguish between the FM and PM, particularly their interrelationship. Then explain the basic concepts of digital data to digital signal conversion. Explain different aspects of ASK, FSK, PSK and QAM conversion techniques. We shall discuss, they will be able to explain bandwidth and power requirement for the transmission of ASK, FSK, PSK and QAM signals. So, as I mentioned in the last lecture, we have discussed about the amplitude modulation. We have started our discussion on analog modulation techniques, and I have discussed in detail the amplitude modulation. And in this lecture, I shall cover frequency modulation and phase modulation. First, let us start with frequency modulation. In frequency modulation, the modulating signal EMT is used to vary the carrier frequency, and because of by the name of frequency modulation, the change in frequency is proportional to the modulating voltage. So, here K is a constant and EMT is the modulating signal, and the frequency deviation this K is known as frequency deviation constant and is expressed in hertz per volt, which may be kilohertz per volt depending on the size of the frequency deviation. And the instantaneous frequency of the modulated signal FIT is equal to FC plus K into EMT, where FC is the carrier frequency. Here this is lowercase is carrier frequency. So, what we find that around the carrier frequency, the frequency will vary, which will be proportional to the modulating signal. This is the basic idea behind frequency modulation. Let us let us take a sinusoidal frequency modulated signal, in which case the modulating signal EMT is a sinusoidal signal. As you can see, EM cos twice pi FMT. That means, here the amplitude maximum, the peak value is EM, capital EM, and this is the cos 2 pi FMT. So, this is a sinusoidal signal. And as I have mentioned, the frequency deviation FIT, which is FC plus KEMT, or I can substitute this to get substitute the value of EMT to get FC plus KEM cos 2 pi FMT, or I can express it in this form FC plus delta F cos twice pi FMT, and you can see delta F is the frequency deviation with respect to the carrier frequency. Therefore, we can represent the modulated signal, that means the modulated signal ST becomes now EC cos phi t. Actually, that here there will be other terms as it is shown here, EC cos twice pi FCT. I think some terms have been missed here. There will be omega CT will be there, omega CT plus phi t. It has to be like this. So there is a mistake here. Now this can be represented by EC cos 2 pi FCT plus 2 pi delta F 0 to t cos 2 pi FMT dt. Now we see we can express it in this way, and then it can be represented at EC cos 2 pi FCT plus delta F by F sin, if we integrate it we get sin 2 pi FMT. So here we see that the amplitude does not change, but the frequency is changing, and here the change in frequency is represented by the modulation index beta, and it is given by beta is equal to delta F by F, delta F by Fm. So it has got relationship with the modulating signal, modulating frequency Fm, and therefore the modulating signal can be represented by EC cos 2 pi FCT plus beta sin 2 pi FMT. So this is the representation of the modulating signal whenever you do frequency modulation, and as you can see beta is the modulation index. Now you may be asking, what is the bandwidth of this modulated signal? In the last lecture we have seen for amplitude modulation, whenever we modulate it by using sinusoidal wave, the bandwidth is equal to twice the bandwidth of the modulating signal, and also however the amplitude varies. And let us see what happens in this case. Because of the presence of this term, we find that the modulated signal will contain various frequency components Fc plus Fm, Fc plus 2 Fm, and so on, many other frequencies. So the bandwidth will be much higher, and this expression for the bandwidth is not very simple. You have to expand it using complicated mathematical expression. So instead of doing that, we can represent the bandwidth by a simplified formula 2 beta plus 1 within quote Bm. So Bt is equal to that the bandwidth of the modulated signal is equal to 2 beta plus 1 into Bm, where Bm is the bandwidth of the modulating signal. And as we have seen, beta is equal to delta F by B, and so which can be represented by Nf Am by 2 pi B, or beta is equal to Bt, bandwidth is equal to 2 delta F 2 B. So what we observe from this simple relationship, that the Fm requires much higher bandwidth than amplitude modulated signal. So the bandwidth requirement for Fm is much higher. Let us see from this relationship, and the peak deviation delta F is 1 by 2 pi Nf into Am Hertz, where Am is the maximum value of Mt, and the value of that bandwidth also depend on the value of beta, and for different values of beta the bandwidth will be different. So what happens in this particular case compared to AM signal? In case of AM signal, we have seen the bandwidth remains 2 Bt or 2 Bm, Bt is equal to 2 Bm, but this is not true here. And another parameter was there, as we increase the modulation index, by increasing the modulation index, we found that the signal gets distorted in case of AM. Does it happen in this case? The answer is no. In this case, as the modulation index, which is beta, increases, the effect of that on the modulated signal is the bandwidth increases, but the distortion does not take place. That means, higher value of beta will lead to higher bandwidth of the modulated signal in case of FM. Now, as we can see in this particular case, that bandwidth requirement is 10 bm. If bm is the bandwidth of the modulating signal and this bandwidth of the modulated signal is 10 bm, that means, suppose we are trying to send audio signal using FM, which has a bandwidth, let us assume 15 kilohertz, then the bandwidth of the modulated signal will be 150 kilohertz. That means 150 kilohertz. So, that will be the bandwidth of the modulated signal. So, in such a case, we find for FM transmission the bandwidth requirement is much higher. So, let us compare the two cases, AM and FM. In case of AM, the band for 15 kilohertz audio signal, the bandwidth requirement will be 30 kilohertz. So, with some gaps on either side, you can have, say, at most, say, you can have another channel at the interval of 50 kilohertz or maybe 40 kilohertz. They can be, the channels can be very closely pressed. On the other hand, in case of FM, the stations has to be at least 200 kilohertz apart. That means, because of higher bandwidth, the number of channels that you can have in FM is limited because of higher bandwidth requirement of the FM signal. Let us look at the power. As the amplitude remains constant, the total average power is equal to the unmodulated carrier power. Here, as you can see, the power requirement is AC square by 2. That means, although AM increases, the amplitude of the modulated signal increases the bandwidth, it does not affect the power. And as a consequence, the transmission power for FM signal is much lower. In case of AM, we have seen that a major part of the energy, half of the energy is required for transmission of the carrier. Then out of the remaining halves, first remaining half of the power, 1/4 goes for half goes for upper sideband, another half goes for lower sideband. But here we see the power requirement is equal to the unmodulated carrier power. So, here you require lesser power for transmission. However, this is possible at the expense of higher bandwidth. So, FM transmission, the conclusion is FM requires higher bandwidth, but lesser power for transmission compared to AM. Let us now look at the phase modulation. In case of phase modulation, we have seen that the modulated signal can be represented by ST is equal to AC cos WCT plus phi t, where this phi phase phi t is proportional to the phase of the signal. The angle WCT plus phi t undergoes a modulation around the angle phi is equal to WCT. That means, around this phase there is change in the phase which is proportional to the modulated signal. So, the signal is therefore angular velocity modulated signal. When the phase is proportional to the modulating signal, that means phi t is equal to NPMT, we call it phase modulation, and here NP is the phase modulation index, just like NF in case of frequency modulation. One interesting observation is this AM and this FM and PM are very closely related. Let us see how they are related. Here we find that if this is the modulating signal MT, and if this is integrated, then pass through phase modulator we get frequency modulated signal. On the other hand, if the modulating signal is passed through a differentiator, then you do frequency modulation, we get phase modulated signal. So, you see you can get frequency modulated signal by using a phase modulator. However, before that you have to do the integration of the modulating signal, and the other one is also possible. You can get phase modulated signal with the help of a frequency modulator. However, the signal, the modulating signal has to be differentiated. So, let us see how exactly it happens. Let the instantaneous frequency of a phase modulated signal is represented by S is equal to E c cos W c t plus k dash m t. Here k dash is a constant. Now, the m t is, let us assume, let m t is derived as an integral of the modulated signal E t. So, E t is the modulating signal, not the modulating signal. Modulating signal, not the modulating signal ET, EMT. So, that MT can be written as k double dash say 0 to t ET, when then with k is equal to k dash into k double dash we get ST is equal to EC cos WCT KT 0 to t ET. So, we can replace the MT here by this with this value. So, this has been substituted in the previous expression and we get this expression. Now, the instantaneous angular frequency of ST, that modulated signal, is 2 pi FIT. So, if you differentiate it, I mean we get from here that as you know, the frequency we can get by differentiating the phase. So, this is the phase, we differentiate it and we get that frequency instantaneous frequency deviation is equal to Fc plus 1 by 2 pi k into Et. So, we find that this waveform is therefore modulated in frequency, because here there is a presence of Et and which varies with frequency. So, this is EMT. EMT was the that signal which varies in time. So, we find that the frequency deviation is taking place. So, whenever you do phase modulation, it also frequency modulation also takes place. In summary, these two together are referred to as angle modulation. In other words, you will find this phase modulation, frequency modulation, angle modulation, these are used interchangeably, because if you look at the waveform, you will find you will not be able to find any distinction. As you can see, this waveform is we have obtained by angle modulation. By looking at this, you cannot tell whether it has been obtained by using frequency modulation or by using phase modulation. And let us see all the three cases, all the four cases together. So, here is the signal to be modulated or modulating signal, this is the carrier signal, and here is the amplitude modulated signal. You see the amplitude is changing and the envelope corresponds to the modulating signal, and here we have got frequency modulated signal and here you have got phase modulated signal. We see the nature of these two signals are absolutely same. Of course, there are some differences in phase between these two signals, that is why they will appear to be identical and their characteristics is same. So, the characteristics of phase modulated signal and the frequency modulated signals are identical. That means, the bandwidth requirement, power requirement for transmission is same for both frequency modulated and phase modulated signals. That is why they together are known as angle modulation. It is they are referred to as angle modulation. Okay. With this, we now change our gear and move to digital data to analog signal conversion. There are many situations in which you have to convert digital data to analog signal. Because why? Because we have to transmit the signal through a analog transmission media. Analog transmission media means it has to be some kind of band pass, it is band pass in nature, or there are many other advantages that we shall get while when we send data in analog form. That means, when the analog signal is transmitted, it has got many advantages that we have already discussed. So, the medium that is available can be analog in nature. For example, telephone line. Telephone line, if we want to use a telephone line for transmission of data, then we have to convert it into analog signal, because the telephone line has been designed to send analog voice signal. So, if we want to send data, we have to convert into analog signal. That is the basis for this digital data to analog signal conversion, and let us see how it happens. So, here we see we have got the digital data in terms of ones and zeros, which is converted into some signal. Then we get the analog signal. So, you see here, according to this data, this is so modulation has been done to get analog signal. Here you see it is analog signal. This corresponds to logic bit 1, this corresponds to 0, this corresponds to 1, this corresponds to 0, this corresponds to 2 ones, then 2 zeros. So, this corresponds to the data that we are transmitting, but instead of sending 1, we are sending an analog signal. For 0, you are not sending anything like that, and this is your analog signal. And there are 3 distinct types of digital to analog modulation technique. One is known as amplitude shift keying, phase shift keying, and frequency shift keying and phase shift keying. And as we shall see, amplitude shift keying and phase shift keying can be combined to have another type of modulation technique, which is known as quadrature amplitude modulation, QAM. So, we shall discuss all these 4 types of modulations, ASK, FSK, PSK and QAM in this lecture. What is amplitude shift keying? Suppose the unmodulated carrier is represented by ECT is equal to capital EC cos twice by FCT. The modulated signal can be written as K EM cos twice by FCT. Here, as you can see here, the amplitude is being changed is proportional to the modulating signal. Now, since the modulating signal can be either 0 or 1, what is possible, this amplitude in one case is A1, in the other case is A2, and as you can see here, the carrier frequencies are same, FC. So, without changing the frequency, we are simply changing the amplitude of these 2 signals. For 1, we are sending one amplitude, for 0, we are sending another amplitude. And a special case of this is whenever this A2 is equal to 0. That means, whenever the data is 1, the amplitude of the modulated signal is A1, and when the data is 0, the amplitude of the modulated signal is 0. This special case is known as on-off keying or OOK. And on-off keying, as we shall see, is susceptible to sudden gain changes, and that on-off keying, however, on-off keying has been found to be very suitable for transmission of data through optical fiber. So, in optical fiber we can say that we use on-off keying. That means, whenever it is 1, we send some light coming from light emitting diode or laser diode, or when it is 0, no light is transmitted through the optical fiber. This is how the modulation is done. So, this is the OAK technique. On-off keying technique is used for transmission of digital data through optical fiber. So, this is how it happens is shown here. This is essentially on-off keying. Now, let us look at the frequency spectrum. If you look at the frequency spectrum, you will find that bandwidth is relatively small compared to AM. In fact, the bandwidth is decided by the bandwidth of the modulating signal. as we know, if it is a square wave sort of thing, then we have the fundamental, the third harmonic and so on. So, apart from the carrier frequency, we have the Fc plus F0, the carrier plus the fundamental frequency of the signal, then third harmonic Fc plus 3 F0. On the other side, we have Fc minus F0, Fc minus 3 F0 and so on. Of course, the other spectral components will have lesser and lesser amplitude. So, if we look at the frequency spectrum of ASK signal, then we can see that if Bm is the overall bandwidth of the binary signal, then the bandwidth of the modulated signal is Bt is equal to Nb. So, on either side we have Fc plus Nb by 2 and Fc minus Nb by 2. So, bandwidth is equal to Nb, where Nb is the baud rate of the modulating signal. So, we see the bandwidth is not really very high whenever we transmit using ASK, it is very similar to AM signal. Now, let us see the frequency shift keying. In frequency shift keying, the frequency of the carrier is used to represent 1 and 0. That means, we are using two different frequencies, amplitude is kept constant. Whenever it is we are sending binary 1, we are using a carrier frequency Fc1. Whenever we are sending binary 0, we are using a carrier frequency Fc2. And whenever we do that, then it has been found that it is much less susceptible to noise and gain changes. One drawback of amplitude shift keying, you see the amplitude is changing, and as a consequence there is a possibility of high noise, and that noise level is so high that it is not possible to identify or to detect the lower and higher level of the carrier signals, or 0 level or little higher level of carrier signals. That is why the ASK signal is susceptible to noise and gain changes of the circuit of the amplifier, but in this case whenever we are using frequency shift keying, it is much less susceptible to noise and gain changes, because we are sending two different frequencies, and obviously because of noise the frequencies cannot get changed, and it can be those two frequencies can be very easily detected at the other end. So, here is an example how exactly it happens. We find that here is your data 1 0 1 1 0 0 1, and this is one carrier with frequency Fc1, say this is Fc1 and this corresponds to carrier Fc2. So, you see whenever it is 1, then we are sending the carrier Fc1, and whenever it is 0, we are sending the carrier Fc2, and here you have got 2 1s. So, we are sending Fc1, 2 zeros to 2 Fc0 2s and 2 Fc1. So, here we can see that that frequency shift keyed signal looks like this. That means, here is your frequency shift keying signal at the what we receive at the receiving end. So, we have two different frequencies Fc1 and Fc2, they are sent alternately depending on the data is 1 or 0. Now, the question is what is the frequency spectrum? As you can see, this is equivalent to sending two ASK signals, one of carrier frequency Fc1, another of carrier frequency Fc2. As a consequence, the bandwidth of the frequency shift keyed signal is much higher. So, this corresponds to one ASK signal, this corresponds to another ASK signal, as if we are sending one amplitude shift keying having frequency Fc1 or F1 here as it is written, or another one with frequency F2, carrier frequency F2. So, these two together will lead to much higher bandwidth for frequency shift keying signal, just like the case for FM signal compared to AM signal. So, here is the frequency spectrum of FSK signal. FSK may be considered as a combination of two ASK spectra centered around FC1 and FC2 as I mentioned. So, the bandwidth is equal to FC2 minus FC1. So, here FC2 minus FC1, then on either side you will have NB by 2 on either side. So, total bandwidth is FC2 minus FC1 plus NB. So, bandwidth requirement is higher in case of FSK signal. Now, let us look at the third variation, that is phase shift keying. In phase shift keying, just like your phase modulation, the phase of the signal will change or will be proportional to the modulating signal. That means, whenever it is 1, we shall send in one phase, and whenever it is 0, we shall send the carrier with another phase, as it is shown here. So, we are sending the carrier with phase shift of pi, that means 180 degree for binary 1, and whenever it is 0, we are sending the carrier without any phase shift, that means here the phase shift is 0. So, the constellation diagram or phase state diagram as it is shown here, that means the corresponding to 0 we find the phase shift is 0, and for 1 the phase shift is 180 degree. So, this is known as 2 PSK, that means 2 phase shift keying, that we are using 2 different phases, that's how we have got this name 2 PSK, 2 phase shift keying. As it is shown here, this is the signal corresponding to 0 and this is the signal corresponding to 1. So, here we see for 0 the phase is 0, you are starting with 0, on the other hand for 1 the phase is 180 degree. So, this is also 1, so phase it is starting with phase of 180 degree, and this is 0, phase is starting. So, you can see at the boundary, whenever it is changing from 0 to 1 or 1 to 0, there is a abrupt phase shift which can be detected at the receiving end, and to identify that this is corresponding to 0 data of 0 and this corresponds to data of 1. So, this is how the phase shift keying done, and this is how a 2 PSK signal is generated and can be sent, and this is the time domain representation. Now, we can extend the basic concept of 2 PSK modulation to have QPSK. In QPSK, what we are doing? We shall be sending 4 different phases. So, so since there are 4 different phases, it is possible to represent 2 bits for each signaling element. So, whenever phase is 0 degree, then it corresponds to bits 0 0. That means, each signaling element is able to send instead of 1 bit 2 bits, and if it is 90 degree, then you are sending data bits 0 1. Whenever it is 180 degree, we are sending data bits 1 0. Whenever the phase shift is 270 degree, data bits are 1 1. So, here is the phase state diagram. For 0 0 it is 0, for 0 1 it is 90 degree, for 1 0 180 degree, for 1 1 270 degree. So, the phase shift occurs in multiple of 90 degree in case of QAM. So, you may be asking, what is the advantage that you have gained by this? Earlier what was happening, in this case you can see the there is a term known as baud rate. If you remember, baud rate is essentially the rate of signaling element. So, here you have got one signaling element, here you have got another signaling element, here you have got another signaling element. So, in case of 2 PSK, the baud rate and data rate is same. Baud rate is same as the data rate. Why? Because you can see here, for one data we are having one signal element, for another data bit we are having another signal element. That is why baud rate and data rate is same. So, but in this particular case that is not true. We find that each signaling element, say corresponding to phase 0, can have 2 bits, and so here the baud rate is half the data rate, or in other words data rate is twice the baud rate. That means the number of signal elements will be half that of the data rate. That means for 2 bits you are getting 1 signal element, and as a consequence you are able to send higher data rate having the same baud rate. That is the advantage of this QPSK. The idea can be extended further. Here as you can see, this is a 8 QPSK signal. Here the phase shift is by 45 degree. So 0 0 0 0 0 1 0 1 0, you can see this is 0 0 0 corresponds to 0 degree, 0 0 1 corresponds to 45 degree, and so on as it is shown in this table. 0 1 0 90 degree, 0 1 1 135 degree, 1 0 0 180 degree, 1 0 1 225 degree, 1 1 0 220 degree, 1 1 1 315 degree. So we find in this case we are able to send 3 bits per signaling element. So in that case the data rate will be equal to 3 times the baud rate, because we are able to send 3 data bits per signaling element. That means per that modulated signal element. As a consequence, for the same baud rate we shall be able to send higher data rate. However, there is some limitation at the receiving end, and the limitations comes because of the ability of the equipment to distinguish small differences of phase limits, and as a consequence the potential bit rate is limited. That means the ability of the equipment to distinguish the small phase shifts leads to a restriction on the maximum bit rate that can be transmitted over the medium. So what is the way out? The another alternative is, apart from changing the phase, we can also change the amplitude. In other words, we can combine change in amplitude and change in phase, leading to what is known as QAM, quadrature amplitude modulation. So in this case it is a combined modulation technique. So QAM can be considered as a combination of ASK, amplitude shift keying, plus phase shift keying. For example, this is your 8 QAM. So in this case, as you can see, we have used 2 amplitude levels. This is one amplitude level and this is another amplitude level, and 4 phase values. So 0, 90, 180, 270. So 4 phase values and 2 amplitude values. As a consequence, we are getting 4 into 2, and that leads to your 8 QAM. And here you have got another constellation diagram or phase frequency diagram. Here you see we have used again 2 amplitudes and 1, 2, 3, 4, 5, 6, 7, 8 phases. So here it is possible to have 2 into 8, that means this is equal to 16 QAM. So we find that for each signal element there is change in phase or frequency. That means you can have 2 different amplitudes and 8 different phases, leading to 4 different bits to be sent past signal element. So we can see you can send at higher data rates. So this is the 16 QAM. So in this way you can keep on extending the number of phase changes and number of amplitude changes. However, you will find that the number of amplitude changes is much lower than the number of phase changes. In other words, detection of phase changes is more easier than the detection of amplitude levels, because amplitude levels usually get corrupted because of noise. The phase changes usually does not get corrupted because of noise. That is why normally the number of amplitude levels is less than the number of phase levels. So, if you see here that the baud rate, for different baud rate, what is the bit rate possible? For ASK, FSK and 2PSK, we find baud rate and bit rate are same. For QPSK, as I have explained, if baud rate is n, then the bit rate is 2n. For 8PSK, as I have explained, for baud rate of n, you get bit rate of 3n. For 16 QAM, for baud rate of n, you get bit rate of 4n. Similarly, for 32 QAM, for a baud rate of n, you get 5 n different 5n bit rates. For 128 QAM, for baud rate of n, you get bit rate of 7n, and for 256 QAM, for baud rate of n, you get 8n. So, in other words, the data rate can be 8 times that of baud rate, and this has very good application in modem. Modem stands for modulator demodulator. So, here what you are doing, it converts digital signal to analog signal using either ASK, FSK, PSK or QM. That means modulation is done at the transmitting end, then at the receiving end by demodulation you get back the original data. So, that is what is done in modem. And say let us consider the bandwidth of a typical telephone line. So, here we find that the bandwidth for voice the bandwidth is 3300 minus 300. So, 3000 hertz, but for data the bandwidth is restricted, that means it is 3000 minus 600. So, you get 2400. So, this is the bandwidth that you get for transmission through telephone line. So, whenever your bandwidth of the channel is only 2400 hertz, then what is the data rate that is possible for transmission through telephone line? Let us now go back to the previous table. So, if we use 16 QAM, then the data rate can be 4n. That means your bandwidth of the channel is 2400 into 4, that means we get 9600 bits per second. So, you see by using 16 QAM, the data rate possible for transmission using modem is 9600 bit per second. On the other hand, if you go for 256 QAM, the data rate possible is 2400 into 8, that means 00219,200 bits per second. So, we see it is possible to transmit at a much higher data rate than the bandwidth of the channel by using suitable modulation technique like QAM, which is a combination of ASK and PSK. So, we find this modulation technique is finding very good use in modems, which we normally use for connecting our computer from home to office or for home to that internet service provider. So, modems have many applications. So, this ASK, this digital to analog modulation technique has found extremely good application in modem. Now, it is time to summarize what we have discussed in the last two lectures. We have discussed about transmission of analog signal, where we use different modulation techniques, amplitude modulation, frequency modulation and phase modulation. We have seen in case of amplitude modulation, there is a maximum limit of the modulation index, that means the value of m has to be 1. If the value of m is greater than 1, then the signal gets distorted. In other words, at the other end it is not possible to recover the signal. However, the power required for transmission, the amplitude modulation signal is higher, and that is why the frequency modulated signal and phase modulated signal, which are combined, which are known as angle modulation, requires lesser power, however at the expense of higher bandwidth. So, FM gives you very high quality signal because it is not affected by noise. AM signals, amplitude modulated signals, which gets corrupted by noise and disturbances, as it is our common experience. We find whenever it is cloudy or it is raining, when there is lightning, there is lot of disturbances. On the other hand, the FM signal does not get that much noise because frequency is not affected. However, the bandwidth requirement is much higher for frequency FM signals. Then coming to the digital data, digital analog signal, we have discussed ASK, FSK, PSK and also QAM, and we have found that ASK is simple, and particularly the on-off keying is very attractive, which has found application in optical communication, where that optical signal is modulated by using this OAK on-off keying, and signal requirement is that bandwidth requirement is less. On the other hand, the FSK and PSK, their bandwidth requirements are higher compared to ASK signal, and we have seen how PSK and ASK can be combined to have higher baud rate for transmission of data, high speed data through the modem. And we have seen there by using lower bandwidth channel, you can send data at a higher speed. So, with this we conclude our lecture. However, there are some review questions. Yes. So, review questions are: number 1, which modulation technique is used in optical communication? Second question is, what are the 3 modulation techniques possible in modems? Why? Third question is, why PSK is preferred as the modulation technique in modems? Fourth question is, out of the 3 digital to analog modulation techniques, which one provides higher data rate? So, these questions will be answered in the next lecture, and now it is time to give the answer to the questions of lecture number 9. The first question was, what are the, again that same mistake, what are the benefits of analog modulation techniques? Answer is, frequency translation achieved using analog modulation helps to provide the following benefits. As I have discussed in detail, it allows you to have antenna of practical size. It helps you to have the advantages of narrow bending. Then it opens up the possibility of sending more than one signal through a media simultaneously through frequency division multiplexing, FDM technique. And later on we shall discuss in detail the multiplexing technique, where we shall see this has some use, frequency division multiplexing. Second question was, what are the possible analog to analog modulation techniques? As I have already discussed, there are 3 possible approaches obtained, particularly modifying the 3 vital parameters like amplitude, frequency and phase, and the modulation techniques are known as amplitude modulation, frequency modulation and phase modulation. However, as you have seen that frequency and phase modulations are very similar in some ways, and that is why they are known as angle modulation. Third question was, what is the bandwidth requirement of amplitude modulated signal? Answer is, the bandwidth requirement of the amplitude modulated signal is 2B, where B is the bandwidth of the analog signals. So, we find that the amplitude modulated signal or AM signal requires lesser bandwidth for transmission. Fourth question was, what is SSB transmission? Why SSB transmission is used? Answer is, in SSB single sideband transmission, only one sideband is sent through the media, neither the other sideband, I mean either lower or upper sideband is sent, nor the carrier is transmitted. So, only one sideband is, carrier is not transmitted and one of the two sideband is transmitted. SSB transmission is used for the following two advantages: lower bandwidth, half the bandwidth of the double sideband transmission, and lower power, and it requires about 1/6 of the power that is required for single sideband transmission compared to double sideband transmission. Question number 5 was, why synchronous detection is not commonly used to recover the baseband signal? Answer is, for synchronous detection it is essential to regenerate perfectly synchronous carrier at the receiving end, and it has to be perfectly synchronous in terms of phase and frequency, which is very difficult to do, and as this requires complex hardware, it is not commonly used. On the other hand, we have already discussed very simple circuit by using diode and RC circuit elements. So, that kind of detector is commonly used in AM receivers. So, that answers all the questions that was given in the last lecture, and with this we come to the end of today's lecture. Thank you.